A very good evening, everyone. This is Pallavi Pujar from Biotecnika. I hope you are revising your all the chemistry and bio sessions, right? All right. So today I am going to deal with the chemical bonding chapter, which is most important as the exam point of view. All right. So the chemical bonding, where you are going to study everything. So before that, just let me wait for the students who are willing to join. So students, join me fast as much as possible so that we can continue the chemical bonding chapter, which is interesting and most important one. So if anybody is there, so you can ping me. Yes, Sneha has joined. Hello, Sneha. So Abhirami Selvaraj, hello, good evening. I hope you are going to build a new bond with Biotecnika today. Yeah, I'm fine, Sneha. What about you? Yes, hi Ram. Okay, students. I hope you are all of you are fine and you are enjoying our live revision series. So we'll start with the chemical bonding chapter. If you have any doubt, just please ping me in the chat box. Okay. And before starting the chemical bonding chapter, I'm going to tell regarding the freebie. And today's freebie will be where the 5 years paper analysis will be available in the description box. You can download it. So you have to stay tuned with me till last minute. Okay, so we'll start with the chemical bonding. Okay, so what exactly chemical bonding? So just by looking at the atoms or elements, we often think, right, whether the atoms are existing stable or else they are reactive, and if they are reacting, then what exactly the molecule is being formed and how it is being formed. So you will get so many questions, right? So why do elements react to form the compounds, and what are the forces are existing between the two atoms, and how you are going to build a new molecule? So that force of attraction is nothing but chemical bond, we can say, right? So for that all, you have to know regarding the atoms, how they are going to build a new bond with respect to another different atom, or else the homodiatomic molecule, we can say, that is two say similar atoms. So just coming to the chemical bonding, so just let's see what exactly chemical bond. So you can see the GIF where it is being mentioned the example of carbon atom, hydrogen atom, and the elementary chlorine and water molecule, right? So oxygen is binding to hydrogen where it is forming new bond with the hydrogen, and that is what we can say a force of attraction between hydrogen and oxygen, right? And similarly, what exactly chemical bond? So chemical bond is an attractive force between the two atoms, which is bringing the force of attraction is bringing the two atoms very closely, right? So it is holding two atoms very closely. So that is what we can say, that the chemical bond, right? So these are what the examples all you can see, that is chlorine atom, hydrogen, and the carbon, that is CH4, methane, and water molecule. Okay, so their existence of the force of attraction between the molecules, then that is fine. Then what happens to the force of attraction, whatever we can say bond, whether there is any type of chemical bond, whether it is covalent bond or ionic bond or else metallic bond, coordinate bond. So there might be some kind of types of the chemical bonds, right? So you have to know what type of bonds are there, right? So just let us see with respect to the types of three major types of bonds. Okay, so the types of three bonds are the chemical bonding, the ionic bonding, covalent bonding, and metallic bonding. So this is what metallic bonding, covalent, and ionic. So what exactly ionic bonding, where the sodium and chlorine, if you consider, so sodium is willing to lose its one of electron and it is giving to the chlorine atom. So chlorine is gaining one electron, where sodium is losing its one of the electron. So sodium is losing and it is attaining +1 oxidation state, and chlorine is gaining one electron from the sodium and it is attaining -1 oxidation state. So what you can observe there? So you can observe that the sodium is completely transferring its electron to chlorine. right? Sodium is transferring its electron completely to the chlorine. Then what we can say, it is complete transfer of electron, so that the sodium attain positive charge and chlorine attain negative charge. So that we can say ionic bond. So two ions are formed. So this is ionic bond. So that is what Na plus and Cl minus you can see. So these are what the NaCl structure you can see. There are so many Na and Cl ions overall, right? And coming to the next bond is covalent bond. So covalent bond is completely different from the ionic bond. Why it is different? Because in ionic bond there was a complete share of, or the complete transfer of the electron, but in covalent bond there will be equal sharing of the electrons between two different atoms, or else between the two similar atoms. So that this is what example ClBr is being given. So Cl and Br you have, so both are sharing one electron, both are sharing one electron, so they are going to form ClBr bond. So this is what chlorine also give one electron and bromine is also giving one electron. So both are giving and it is forming covalent bond. So wait, the equal sharing of the electrons will be possible to form the covalent bond, and example is ClBr. Okay, and coming to the last one is metallic bond. So metallic bond is where the bond which is formed between the two metals, we call it as a metallic bond. So now just let us look at all these type of bonding in brief. Okay, so coming to the covalent bond, so previously I had given example with respect to ClBr, right? So now you can see here the H2 molecule, homodiatomic molecule example, right? So H2 molecule, if you look at the molecule overall, the hydrogen which is carrying one electron here and this another hydrogen which is carrying one electron, so both are sharing one electron and they are going to form one new bond. That is what covalent bond we can say. So the bond is formed by sharing of the electrons. So each one of the atom is sharing one electron and it is going to form the covalent bond. That's what we can say covalent bonding. And the covalent bonding will be always possible between the two non-metallic elements or of similar electronegativity. Okay, so there will be not that much of electronegativity difference between the two atoms when you compare with the ionic bonding. So in case of ionic bonding, what happens, the electronegativity will be completely different between the two atoms. Suppose you consider NaCl as an example. So Na, whatever the electronegativity it has, it is less compared to chlorine. So chlorine is most electronegative element. So this is halogen, right? So that is what the covalent bonding overall we can say. And other than this example H2, what example we can give? We can give O2, CO2, that is carbon dioxide, C2H6, water, and SiC, that is silicon carbide. So these are what the covalent bonding having molecules. And next bonding type is ionic bonding. So just let us look at the ionic bonding, how exactly it is. Before that, you have to know there must be existence of some polar nature in the covalent bond, right? So that we can classify like non-polar covalent bond and polar covalent bond, right? So the polar covalent bond is where you can see here, this is what HCl I have given the example, and previously what I have explained, that is regarding non-polar covalent bond, where the electrons whatever you have shared between the two atoms was completely equal. But in case of polar covalent bond, the electronegativity part comes. Because of that reason, there will be slightly existence of the polar nature in the covalent bond. So polar covalent bond is why, because if you consider hydrogen and Cl example, hydrogen electronegativity is less compared to that of chlorine, right? So chlorine is most negative and it is try to withdraw or pull the electron towards itself. And because of that reason, what we can say, there existence of polar covalent bond overall in the molecule. And this is what you can see here, the hydrogen atom, how it is approaching towards the fluorine. So you can look at this GIF overall, where the hydrogen, after losing some amount of electron density, it is bearing partial positive charge, and the chlorine or the fluorine, if you look at the example, which is bearing partial negative charge. Okay, so this is polar covalent bond. And what happens if we compare with the ionic bond? So ionic bond is completely different, where you are completely transferring the electron. So this is what the example you can see, the Na plus, where the sodium is losing one of its electron and it is attaining Na plus, that is +1 oxidation state, and where the chlorine is gaining one of the electron and it is attaining negative charge, that is Cl minus, -1 charge. So this is what the ionic bond and non-polar covalent bond. So these all differences you must know. Okay, now coming to the next part of bonding is ionic bonding. So in case of ionic bonding, as you can see overall, okay, so the ionic bonding, where the bond is formed between two atoms, where one of the atom will be transferring electron completely. Okay, so this is what you can see example of NAF. So NAF or else NaCl also you can say. So Na is losing one of its electron and attaining +1 oxidation state, and fluorine is gaining electron and it is attaining -1 oxidation state. We can say as F minus. Okay. Now coming to where existence of these ionic bonds. So ionic bond will be formed between the metals and non-metals with very different electronegativity, because there is more electronegativity difference. Because of that reason, what we can say, their existence of the ionic bond. And why especially when there is specially this electronegativity difference, so that type of molecules will be able to conduct the electricity. So these are what the conductors and have high melting point. So example for this ionic bonding, where we can say NaCl, CaCl2, K2O. Okay, and now coming to next part of the bonding chapter is where the factors which are affecting ionic bonding. So we know that yes, there might be existence of the ionic bond in the molecule, but what all the factors are affecting in order to form the ionic bond formation, like the what molecules are going to form the ionic bond and how exactly they are affecting. So the first factor you are going to study is low ionization energy. So low ionization energy, where you are going to apply some minimum amount of energy to lose valence electron. So you can see this electron, whatever it is completely uh, glowing, right? So this is where the electron is, where I am going to remove the valence, means this electron I am going to remove from the valence shell. So that is what the valence electron we can say. So you are applying some amount of energy and you are removing it, right? So the amount of energy whatever you are supplying, if it is less, then we can say there will be easier the formation of the ionic molecule or the ionic bond, we can say. If higher the IE you are providing, then there will be where the amount of energy whatever you are supplying to remove the valence shell itself, means the valence electron from the valence shell itself, then it will be like how the ionic bond formation will be very less, where it is not faster as we compare to the low IE consisting of the molecules. Okay, so next part is where the higher lattice energy. So lattice energy, where whenever you are forming any ionic bond or ionic molecule, some amount of energy will be released, right? So that amount of energy whatever we can say as lattice energy. So if there is more amount of lattice energy is released, then we can say that there will be more easier to form the ionic bond. And lastly, the last factor is high electron affinity. So any atom, if it has the tendency to accept the electron vigorously, then we can say it has the tendency, means it has the more tendency to form the ionic bond. So that is what three factors which are affecting the ionic bonding. One is low IE, and secondly you have the high lattice energy, and thirdly you have high electron affinity. So these are what three factors which are affecting ionic bond formation. Okay, so now coming to the next part, where the metallic bonding. So metallic bonding, as you can see overall, so the bond which holds two metals together. So the force of attraction which is holding two metals together, we call it as a metallic bonding. So this is what overall you can see the positively charged ions, and where the sea of electrons you can see, right? So whatever the small circles you can see. So those are nothing but the electron cloud which is moving in the metal. So this is what the metallic bonding we can say, and it is mainly formed between the atoms of metallic elements and the electron cloud around the atoms we can say. So there will be more of the electrons around the atoms. And what examples you can give? The example you can give as sodium, iron, aluminum, and gold and cobalt. So these are what the few examples with respect to metallic bonding. And now coming to the next part of chemical bonding is formal charge. Okay, so what exactly formal charge? So formal charge is the difference between the number of valence electrons of an atom in its free state, or else when we write its Lewis structure. So when we write the Lewis structure, so exactly you will get to know how many electrons are involved in the bond formation, right? So how many electrons are involved in the bond formation? Along with that, you are going to check the formal charge. So in order to know the formal charge, there is one formula where the formula is looking like this, where it will be having the formula charge where you can see here, that is equal to electrons how many are donated in a molecule, and where electrons are shared divided by 2 minus unshared electrons. Suppose you take an example of methanol. So in the example you can see this is methanol. Okay, so in case of methanol, where the two that is one carbon and one oxygen you have, and four hydrogens you have. So one carbon is bound to three hydrogens and oxygen has bound to one hydrogen. So now you have to calculate the formal charge of oxygen. So like that, you have to calculate for each and every atom of a molecule. So for oxygen also you are going to calculate, for carbon also you are going to calculate, and for hydrogen also. So right now, in case of oxygen, if you consider, so how many electrons oxygen has? 6 valence electrons it has, right? So where it is donating. And apart from that, how many electrons are being shared overall? So 4 electrons are being shared, and divided by 2 you are going to do. This is what you have to check here. And then 4 unshared electrons you have. So if you overall calculate, so that will be like how? So that will be 4 minus 8 divided by 2 minus 0, that is equal to 0 you have, right? So 4, so 2 ones are 2 fours are, so 4 minus 4, so overall you will get 0 as an answer, right? So formal charge is what? It is 0 in the methanol molecule. Like that, you have to calculate for carbon and hydrogen also. So if you calculate for carbon, so what you are going to get? So that you will get 6 minus 4 divided by 2 minus 4 is equal to 0. So again you will get what? The answer as 0. And then what you will get? You are going to calculate again for hydrogen. So for hydrogen you are going to get 0. So like that, you have to consider any molecule, and you are going to calculate overall the formal charge with respect to any atom in a molecule. So this is what formal charge concept. Now coming to the next part of chemical bonding is Fuzziness rule. So this is most important, because based on this Fuzziness rule only you are going to know how exactly the covalent character exists in case of ionic bonding. Okay, so before that, just let me know how many students have joined. Yes, okay. So Pradeep has joined right now. Very good evening. Okay. Okay, students, so like this, you only join me faster so that you can revise your chemical bonding chapter in easiest way, and you are going to clear your every single doubt. Okay, so coming to the Fuzziness rule. So Fuzziness rule, where the Fuzzen scientist first time he get to know that there might be some existence of covalent character in case of ionic molecule, right? So the Fuzziness rule, according to him, he says that ionic bond, whatever it has some covalency in it. Okay, so it has some covalent character, and because of that covalent character, what we can say, their existence of the covalent character in so many alkali chlorides and all, you are going to study in detail with respect to the examples. Okay, where the postulates you are going to study, or the conditions we can say with respect to Fuzziness rule. So Fuzziness rule is mainly related to covalent character in ionic bond or else ionic compounds you can say. And mainly here you are going to consider overall the degree of polarization and the polarizing power and the polarizability. So polarizing power is what? the cation has the ability to polarize the anion. In the sense what, the cation and anion both are mainly there will be electrostatic attraction between the positive and cation, right? So now, so the polarizing power is related to cation and polarized ability is related to anion. So anion will be able to polarize itself as the cation comes near to it. Okay. So in case of this picture, you can see, okay. So in this picture, as you can see, firstly in the beginning, there will be only cation and anion, right? So only cation and anion you can see, and further there will be some kind of polarization between this cation and anion, and then what you can see, the polarization of anion and cation, where the anion is deformed, the electron density is deformed overall in the anion, and this is what the structure. If you can see the anion here, it is little bit where it is where the wider structure you can see, right? And when you consider the third one, where you can see the polarization, the complete polarization of the anion due to cation, we can say there will be polarization in a cation and anion. So overall what we can say, their existence of covalent character overall in a molecule, right? So with respect to this Fuzzen's rule, you have some conditions or else postulates we can say, and just let us look at it one by one. Okay, so the postulate first one is what, the size of cation. So whenever you consider the covalent character with respect to size of the cation, and then you have to compare, means if you are going to increase, if you are going to increase the cation size, what happens, if it is less, then what happens. Okay, so coming to the size of the cation, so in the example, as you can see, the beryllium, magnesium, calcium and strontium, barium is being given. So we know that when you go from barium to beryllium to barium, so size of the atom will be increasing, right? So if the size of the atom is increasing, then what you can say, the covalent property will be decreasing. So apart from this, what we can say overall, whenever any cation has lesser size or the smaller size, we can say the covalent character will be more in that molecule. Okay, so just let me repeat it once again. Whenever any atom has less size, okay, less size, then covalent character will be more. So the cation with smaller size will be always having higher polarizing power, and it is able to polarize the anion, and the anion will be undergoing more polarization. So that is what, higher the polarization, more will be the covalent character in a molecule. That's why when you compare with respect to cation size, that is from beryllium to barium, the beryllium having lesser size or the smaller cation, and where barium you can see this is bit bigger compared to remaining all elements, right? So because of that reason, what you can say, the covalent property will be increasing towards beryllium rather than barium. So first condition you got to know that smaller the cation size, higher will be the polarization, and there will be increase in the covalent property. All right. So coming to the next condition is size of anion. So as we consider the size of cation, and similarly the anion size also matters here. Okay, so the anions, when we compare, it is bit reverse here. So in case of cation, the cation size has to be smaller, but in case of anion, it is reverse, where the anion size has to be bigger. So the anions with larger size, having higher polarizability, then what we can say, the covalent character will be more in that molecule. So in case of halogens, if you consider fluorine, chlorine, bromine, iodine, where as we go down the group, the atomic size is increasing in the periodic table, then what we can say, the anion, that is iodine will be having higher polarizability, and it is causing more increase in the covalent character in a molecule. So F minus, when we compare with the I minus, F minus is having lesser atomic size, and then we can say it is where it is mainly, it shows the lesser covalent character in a molecule whenever we have F minus as a anion. So this is what with respect to anion. Okay, and now coming to the next part is charge of cation or anion or both. Okay, so size we compared with respect to anion and cation. So now you are going to consider anion and cation charge. What happens if we increase the charge of cation and anion? So when there is increase in the charge of cation and anion, so both are enhancing with each other, and because of that reason, what we can say, there will be increase in the covalent characters. That's why the example is being given with respect to cation charge, that is Na plus 1 and magnesium plus 2, where you have further aluminum plus 3, right? So aluminum plus 3 you have. So Na plus 1, magnesium 2 plus, and aluminum 3 plus. So aluminum is having higher charge, right? So because of that reason, we can say the cation charge, where the cation which is having more charge, then we can say overall the covalent character is more in that molecule. So this is what with respect to charge of cation and anion, right? Now coming to the next postulate is what? The number of electrons in the outermost inner shell of cation. So cation, so in case of this example, if you consider here, so this is mainly the chlorides of copper, silver and gold, and sodium, potassium and rubidium. So the copper, gold and silver, whatever the halides you have, so they have more tendency to increase the covalent character rather than the sodium, potassium, rubidium. Why? Because whenever you have the pseudo noble gas configuration having molecule, so they are able to increase the covalent character rather than the elements which are having only noble gas configuration. Why we call pseudo noble gas? Because ns2 np6 we call it as noble gas configuration, right? If it is pseudo noble gas, in the sense what, you are going to add the d10 configuration also there, right? So that is what we can say, this is pseudo noble gas configuration we can say. And noble gas, where only you are going to consider ns2 np6. So whenever any molecule or any atom which is having pseudo noble gas configuration, then we can say it is able to increase the higher, means it is able to increase the polarization in a molecule, and it is going to increase the covalent character overall, right? So this is what the number of electrons in the inert shell of cation. Okay, so now coming to the next part of condition is dielectric constant. So dielectric constant of a medium, whenever we consider, so in normal, in polar medium, we know that the dielectric constant will be high, right? So when we compare with respect to non-polar medium, with respect to polar medium, the non-polar medium having the molecules where the covalent character will be more, apart from the polar medium having molecule. So that is what with respect to that is dielectric constant of a medium. Okay, so dielectric constant medium, where the non-polar medium with the covalent character of a compound increases. So in a non-polar medium, the covalent character will be always more compared to the polar medium. Okay, so this is what with respect to overall the Fuzzen's rule conditions. Now what exactly we can apply, the application part of the Fuzzen's rule, what you are going to do with respect to Fuzzen's rule. So specifically, when we want to know specifically the solubility, melting point and ionic character, so with respect to these all, with example I have explained you, right? Copper and Ag, gold, where the halides, along with that the cation size and all. So overall there is more application part when we consider this Fuzzen's rule with respect to solubility or the ionic character, or else the melting point, boiling point and all. So there are some exceptional cases also whenever you go on study with respect to application part. So right now, so with this we are going to end the Fuzzen's rule. So now we'll move on with respect to the remaining part of chemical bonding, that is covalent bond theory, so which are most important. And overall the covalent bonding, it mainly the structure of a molecule and the shapes of the molecule, and thirdly the third thing where you are going to consider the bonding in a molecule. So how exactly a molecule is having bonding and how exactly the bond is formed. So what type of bond you have, whether it is sigma bond, pi bond. So those all concepts has been studied in case of these covalent bond theories. Okay, so I hope I am revising all the chemical bonding concept. Yes students, if it is yes, just ping me in the chat box. Okay, so covalent bond theories. So three theories you have. One is Vsepr, valence bond theory, and molecular orbital theory. So VSEPR theory, why you have to study? Because VSEPR theory mainly it predicts the shapes and geometry of molecule, shapes and geometry of a molecule. And when you study the VBT, so VBT where you are going to study how exactly the atomic orbitals are formed and how you are filling the electrons into the atomic orbital, and atomic orbitals further if they are going to form the molecular orbitals where the new bond is being formed. So that mainly explained by the MOT. Okay, so valence bond theory where the hybridization of a molecule you are going to study, and where the MOT, if you consider the MOT where you are going to consider each and every molecule where along with the bond order, and how exactly the molecular orbitals are formed by considering the atomic orbitals, each and every concept you are going to study here. Okay, so now coming to the next part is covalent bond theories part, that is VSCPR you are going to study. So as I have told, VSCPR theory mainly predicts shapes and geometry of molecule, right? Shape and geometry of molecule. So when we compare the shapes and geometry, why there will be a change in the shapes or the geometry of a molecule? The original geometry will be tetrahedral, but because of the presence of lone pair on a central atom, there will be change in its shape, right? So those type of structures, how it has come. So just let us look at it. Okay, so why the method which predicts the shapes and geometry of a molecules where you are going to study the VSEPR theory. So the two postulates you are going to consider here. So one is the covalent molecules assume geometry that minimizes the among the electrons in valence shell of atom, and the second postulate where the shapes of the molecule can be maybe it will be predicted from Lewis structure. So Lewis structure where when you consider any molecule, so you are going to calculate how many electrons are being shared between the two atoms, and you are going to show it by dotted structure, right? So that is what the Lewis structure overall you can say. And where the main general trend in case of VSEPR theory you have to remember, so just I am marking it here, I'm marking it here. So you have to mug up this, or else just try to understand. This is not that much difficult. So just let me tell you why it is given the priority order as lone pair first, then lone pair, then bond pair. Why it is being given? Because when you consider any molecule, okay, any molecule. Suppose I am forming A2 molecule. Okay, so I am forming A2 molecule. So their existence of only one bond. If only one bond is there, then we can say bond pair, right? So along with that, if their existence of lone pair of electron. Okay, so if their existence of lone pair of electron, then what, how you can say? So just assume that, so on A one lone pair of electron is present, and A again another atom where another lone pair of electron is present. So these lone pair of electrons which are not involved in the bonding, they occupy more space. Okay, so they occupy more space. Because of that reason, what we can say, the repulsion between these two lone pair of electrons will be more compared to the lone pair bond pair, or else bond pair. So when it comes bond pair, suppose this A is attached to some more atom, like suppose their existence of the two bonds, then there comes the concept of bond pair repulsion. And bond pair lone pair bond pair, when it comes, so these electrons along with this bond, there will be lone pair bond pair repulsion. If the two atoms which are consisting the lone pairs, then we can say it is lone pair repulsion. So why lone pair repulsion is kept first order, where why it is kept? Because the lone pairs which are present around the atom, they occupying more space compared to the bond pair, because they are not involved in any atom, in any bonding with respect to the atom, which are free, right, which are free to each other. And then we can see the repulsion will be more with respect to lone pair compared to lone pair bond pair. So this is what you have to remember. Okay, this is what you have to remember. Lone pair is first, then lone pair then bond pair. Okay, so the priority order you have to keep it. Now we'll move on further with respect to VSCPR theory, where the shapes of the molecules or the geometry of the molecule overall you can see those are five geometry. The basics we can say, this is linear, where trigonal, planar, on this is where tetrahedral you have trigonal, bipyramidal, and octahedral, right? So these are what the basic shapes what we have with respect to molecules. But because of the presence of lone pairs, these geometries are going to change, means the shapes of the molecules are going to be changed. So just let us look at one by one with example. All right, so coming to the first one is the molecule which is consisting of the linear electron group arrangement. Okay, so the linear electron group arrangement, when we compare the simple example where the molecule will be AX2 type, AX2 where A might be anything. Suppose I consider BF2 where it is linear, right, which is linear, and where its geometry will be linear again, and it is not going to change because on beryllium there is no any lone pair, right? If there are lone pair, then existence of the change in the shape of the overall molecule. Okay, so this is what with respect to with respect to linear electron group arrangement. Apart from that, apart from BF2, you can give the example of hydrogen cyanide, carbon disulfide also. So coming to the next example is trigonal planar electron group rearrangement. Here you can see two types of molecules where AX3, AX2E. So AX2E is nothing but lone pair of electron here. Okay, so E is nothing but lone pair of electrons, and here you are going to consider first one is AX3. So AX3 is the simple molecule where you can see SO3, BF3, NO3 minus or CO3 2 minus. So where it will be having simple trigonal planar geometry. Along with that, if you consider any molecule which is having lone pair of electron along with the AX2E type of molecules, if you consider, then it will be having lone pair of electron. Because of that reason, we cannot say this is trigonal planar, but it is bend shaped. This is bend shaped molecule, and the examples you can give as SO2 and O3, PbCl2 and SnBr2. So these are what the examples to the AX2E type of molecules. Okay, so now coming to the next type of molecules, as you can see, that is tetrahedral electron group arrangement. So first, where the three types of molecules you can see, that is AX4, that is normal one, and AX3E, AX2E2. So AX4, where you can give the example of simple CH4, right? That is methane molecule where it will be having tetrahedral geometry. So you can see this is what the tetrahedral it looks like. And apart from that, AX3E, where one lone pair of electrons will be there. So this is what you can see overall, that is it is attaining trigonal pyramidal structure instead of tetrahedral. So it has to be AX4 type, right? But their existence of lone pair of electron and its geometry or the shape is changing to trigonal pyramidal. Apart from that, you have AX2E2, where AX2E2 where two lone pairs of electrons, so two pairs you can see, then you can see the overall structure is changing to bent shape. So this is bent shape of molecule where you can see the simple or good example is H2O, right? So H2O you have. So where you have lone pair here also, right? So where we can say the H2O is having bent shape. Now, apart from this, what type of molecules we do have? Further, we do have again trigonal bipyramidal electron group arrangement. So if you consider in case of trigonal bipyramidal, so their existence of AX5, AX4E, AX3E2, AX2E3. So you're going to increase one by one. So as you're moving towards the 6 and 5 electron pairs, right? So in case of trigonal bipyramidal, if you consider this is AX5, you can say, and the example you can give as PF5, that is phosphorus pentafluoride, right? And AX4E type, where one lone pair of electrons present. So there you can see it is looking like seesaw type. This is looking like seesaw type, and then we can say this is AX4E type of molecule, and its geometry is geometry where the trigonal bipyramidal 2, it is looking like seesaw type. Now coming to T shaped, where AX3E2 type, and the example you can give ClF3 and BrF3, right? And AX2E3 is the last molecular type where you can give the example is XeF2. Okay, XeF2, xenon difluoride. So these are what with respect to trigonal bipyramidal electron group arrangement. And apart from this, their existence of octahedral electron group arrangement. So the first one is what? AX6 type. AX6 type, where octahedral simple we can say SF6 you can have, right? So SF6 where you are going to have everywhere fluorine. So this is what example you can give, simple one. And AX5E where you have one electron pair here, one electron pair you have, and square pyramidal you can see the shape. And the examples you can give: bromine pentafluoride, BRF5 or TF5 minus, and XeOF4. And apart from that, is there any other one? That is AX4E2 type, right? And here the example you can give as XeF4, and it will be having square planar shape overall. So overall, when you consider the 6 number, like 6 valence electron, if you consider, where the octahedral geometry you must get, but apart from that you are getting different shapes because of what reason? Because of the lone pair of electrons which are present overall on the central atom, right? So this is what with respect to Vsepr theory until octahedral electron group rearrangement. So there are so many molecular shapes and you have to revise it thoroughly. Now coming to the question answer session, where you have to answer me. I hope I have cleared you the VSEPR theory. So just let me know what answer you will get for this question. So the question is like this: which one of the following is planar? So they are asking regarding the molecule which is planar. So just pick the answer. Let me know answer what you will get. Faster, students. So the option A is like XeF4, XeO4, XeO3F, XeO3F2. So 4 options you have. So just ping me faster. I hope you will answer it very well. So just you have to look at the structure according to the VSEPR theory and let me know what answer you will get. Okay. Someone Daytech has answered it is A. What about others? Okay, so let me tell you the answer. So the option A is correct here, XeF4. So these remaining all will be having trigonal bipyramidal type of structures, and where the XeF4 will be looking like this. So already I have told the square planar, right? So where it will be having lone pair here, and 4 side it will be having 4 fluorines, right? So this is what square planar type of structure. Okay, so coming to the next example, in NO3 minus ion, the number of bond pair and lone pair of electron on nitrogen atom are. So in order to answer this question, you have to know the structure of NO3 minus ion. So try to draw NO3 minus ion, then just let me know what answer you will get. How many electrons are remain on the nitrogen atom? Yes. So you have 4 options: 2 and 2, 3 and 1, 1 and 3, 4 and 0, in the sense bond pair and lone pair they have given. So you have to answer me what you will get. So make it quick. Okay, so the answer is like this. So if you look at NO3 structure, so nitrogen, which is bound to 3 oxygens, right? So 3 oxygens. So Dielectric, he has answered it as B. All right. Okay, so NO3, where one side it will be having N double bond O, another side 2 oxygens are present. So you can show the charges overall, and that's what you can show like this, the charge overall. So you can show overall like this. So the charge will be minus, you can show like this, right? So nitrogen, if you consider, so it is involved with oxygen, where 4 bond you can see, 4 bond you can see, so 4 bond pairs you can say, and nitrogen is not having any lone pair of electron in NO3 minus ion, then we can say option D is correct here. All right, so the answer has to be D here. Now coming to the next part is valence bond theory. So as I have told previously, VSEPR, we got to know exactly shapes and geometry of the molecules. So now your duty is to know how exactly the atomic orbitals are combining. So what type of overlapping you have. So VBT is mainly explaining regarding the electrons, how exactly they are filling the atomic orbitals and how they tend to form the molecules. Okay, so how they tend to form the molecules. So the four postulates you have with respect to VBT. So according to first postulate, so the first postulate states that the two half-filled valence orbitals of two different atoms are going to combine with each other and they are going to form covalent bond. So just consider you have two different atoms. So this is A and this is B. So this has one electron and this has one electron. So these both are half-filled atomic orbitals, right? Half-filled atomic orbitals are going to combine and it is going to form new bond. So this is what the new covalent bond is being formed. Then what we can say, this is first postulate of VBT, right? And then if any atom has extra electrons, means it has any unpaired electron on it, then we can say it is able to form more than one type of bond. So it is able to form more than one bond. Then what we can say, overall we can say that the second postulate, more than one unpaired electron, then more than one bond can be formed overall in a molecule. And the third postulate is that the covalent bond is always directional, in the sense what it is with respect to the symmetry. And apart from that, the overlapping nature. So the extent of overlapping is also important whenever you are going to form molecule, because so how exactly the atomic orbitals, like the two atomic orbitals are overlapping with each other, then you are going to form the molecule, right? So the extent of overlapping is also most important whenever you consider the molecule formation. So these are what the four postulates of VBT. And then let us look at the types of overlapping. So how many overlapping you have? So the first overlapping you can see, this is SS overlapping. Okay, so two s orbitals are overlapping with each other. Two spherical shape s orbitals are overlapping with each other. So then we can say it is SS overlapping. And the second overlapping is what? SP overlapping. So this is what p orbital you have. So this p orbital is combining with s orbital, and this overlapping we can say as SP overlapping. And nextly you have PP overlapping. So PP overlapping, you have one more thing, that is sideway overlapping also. So this sideway overlapping, as you can see, okay, so this is what the sideway overlapping overall you can say. So two p orbitals will be there. So just let me show here, two p orbitals will be there. So where they are going to overlap like this. So this is what the sideway overlap we can say. So SS, SP and PP overlapping. So there are four types of overlapping we can say. That is what with respect to sigma and pi bond formation. So overall sigma and pi bond can be formed between the two atoms in order to form molecules. So now coming to the next part of chemical bonding is hybridization. So now you have an idea regarding the VBT theory, where how exactly the two half-filled atomic orbitals are combining with each other and they are going to form molecule, right. So now hybridization is what? You are going to intermix the atomic orbitals, right. So you are going to intermix the atomic orbitals and you are going to form new molecule. So if more than two atoms are involved in a molecule, then the shapes of the orbitals must be matching, and the shape of the bonds that are needed, like trigonal or tetrahedral, etc., and the atomic orbitals do not have these shapes and must mix to achieve needed shapes. So what they will do, they will mix in such a way that they have to attain more stability to the molecule, in order to, like, they will change their shapes also, like trigonal, tetrahedral, so many basic shapes you have studied, right. So now just let us look at the hybridization. So how many types you have? So there are three, where one is sp3, sp2 and sp. So sp3, where one carbon if you consider, okay, so one carbon if you consider, it is gone bonding with four hydrogens, right. So CH4 as an example if you consider. So this is what sp3 hybridized molecule. So one s orbital and three p orbitals both are combining, and all are combining, and it is giving me sp3 hybrid molecule orbital, okay, molecular orbital. Same way sp2 and sp hybridization you have. So now just let us look at it one by one with example. So coming to the example, one is BeCl2. So BeCl2 is an example for sp hybridization. So we know that beryllium is 4 atomic number, right. So what you can say, 1s2, 2s2. 1s2, 2s2. So 2s, so s orbital 1 you can show. One you can show. Apart from that, you will be having next p orbital, right? So just let me consider it as 2p. And now 2s2, it is what? Ground state electronic configuration of beryllium atom. If you consider its excited electronic configuration, that is excited state, if you say, so in excited state, so 1s2 are the core electrons, are they are not involving in the bond formation, but 2s2 where the two electrons are present, they are involved in the bond formation, right? So now you have two electrons. So two electrons in the ground state you have, but in excitation state where you are applying some energy, so one of the electron will be exciting to the next level, that is 2p orbital it is. So you can show, so s and p. So this is what? 2s and this is 2p. So this is what? 2s 2p, right? So overall where we can say the sp hybridization with respect to BeCl2, where the beryllium and chlorine both are having, that is 2s of beryllium and 2p of next chlorine, both are combining and it is giving me sp hybridized molecule, right? So this is what overall we can say with respect to BeCl2, and it attains the geometry as linear geometry. So this is what you can see overall, right? So this is what you can see overall, the structure or the geometry of a molecule. And now coming to the next example is with respect to sp2 hybridization, that is BF3 as an example. So in case of BF3 also, again we know that boron is 5 atomic number, right? So 5 atomic number you have. Now what you can see, that is 1s2, 2s2, 2p1 you have. So 1s2, 2s2, 2p1 you have. So similarly again you are going to consider like this, that is 2s2, 2p1, 2s2, 2p1. So just let me consider 2s2, 2p1 you have. So s orbital which is having 2 electrons, so it will excite to the p orbital, second orbital. So now 2s orbital will be having 1 electron and 2p will be having 2 electron. So now it will combine with respect to fluorine atom and it will give me sp2 hybridized molecule overall. Okay, so sp2 hybridized molecule where its geometry will be what? Trigonal planar. And this is what BF3 we can say. And now coming to the last, sp3 hybridization, where tetrahedral molecule you can get, that is CH4. The simple example you know, right? Again here you have the carbon where you can say its electronic configuration will be 1s2, 2s2, 2p2, right? So 2s2 where 2 electrons you have, 2p2 where here you have 2 electrons. So you will apply some amount of energy and the s orbital electron which are 2, right? So one electron will be exciting to the vacant p orbital and now it will be having how many? 3 electrons here, right? So 3 electrons and here 1. So overall it will be sp3, right? So overall sp3, and then we can say the molecule is sp3 hybridized, right? So overall this is what with respect to sp, sp2, sp3 hybridization with respect to all the molecules. And this is what the geometry it looks like, you can see here. Okay, so this is what you can see overall the geometry. I hope it is visible, right? So sp3 carbon which is attached to 4 hydrogen atoms. Now coming to the next part. Okay, so just before that let me confirm whether students are you understanding. Okay, so coming to the next important part is molecular orbital theory, that is MOT. So we know that now VBT, then VSEPR. Now you have to know how exactly the bonding is there in a molecule, whether it is anti-bonding or else bonding, whether the anti-bonding is higher in energy or else lower in energy. So those all concepts are mainly studied in MOT. So when you consider two atoms in MOT, that is molecular orbital theory, so the two atoms, whenever they come together, their atomic orbitals they interact with each other and they will form two types of possible molecular orbital. One is lower energy bonding molecular orbital. Another one is higher energy anti-bonding molecular orbital. Right. So this is what you can say with respect to the diagram which is showing the superposition of the two 1s orbitals. So these are what 1s orbital of atom A and 1s orbital of atom B. So it is going to form 1s sigma bond, that is, and that is bonding molecular orbital where the energy will be less. So energy will be less when you consider BMO also we can say indirectly. So we can say BMO in shortcut. Okay. So BMO is bonding molecular orbital where the energy will be less. And when you consider the anti-bonding molecular orbital, and with respect to psi, this is the wave function we will predict the molecular orbital theory, right? So now coming to this is what we can say it as ABMO, that is anti-bonding molecular orbital. So whenever you consider the two atoms and they are going to interact with each other and they are going to form two types of bonding molecular orbital, that is molecular orbitals. One is bonding, another one is anti-bonding, and bonding will be having lesser energy and anti-bonding will be having higher energy. Okay, so this is what with respect to ABMO and BMO. Now coming to the next, where the how many conditions we do have with respect to BMO, that is MOT. Okay, so MOT whenever you are going to study, so first thing you have to keep in your mind that the combining atomic orbitals must have same energy or else nearly same energy. So if you have one atom as A, another atom as B, so now atom A will be having 1s atomic orbital and atom B where it will be having 1s and 2s, but you are going to form 1s and 2s interaction, right? So if you are doing this type, then it is not possible because 1s is where lower in energy and 2s is higher in energy. Because of that reason, what we can say, the B atom whatever you consider, it must interact with the 1s orbital. So 1s orbital of atom A will be interacting with the 1s orbital of atom B, then it is able to form, or it will be able to overlap, and it is gone forming the molecule. And nextly, where the combining orbitals must have the same symmetry about the molecular axis. Suppose you consider the 2pz orbital of atom A. Okay, so the same example I am taking, 2pz, and B where you are considering with respect to its other orbital, that is px. If you consider, okay, if you consider 2px. Okay, so overall where you consider with respect to the symmetry where the symmetry has to match whenever you consider with respect to the two atoms each other. If the symmetry is matching, then they are going to form. So 2pz or 2px if you are going to form, then it will not form. Instead of that, the 2pz you have to consider and they will be able to form the bond. And now coming to the last point, where that is with respect to extent of overlapping. So greater the extent of overlapping, then there will be more the electron density distribution. So the electron density is distributed between two atoms, then what we can say, the overlapping is at its greater extent, right? Then we can say the molecule is formed completely. So that is what the few conditions you have with respect to MOT. Now coming to the next part is the important points you have to remember regarding MOT. So the thing that whenever you consider the bonding molecular orbital and anti-bonding. So here NB is with respect to bonding molecular orbital. That is just I will write it as BMO. I hope you will understand what exactly BMO. So BMO is nothing but it is bonding molecular orbital, and Na is what? It is ABMO, that is anti-bonding molecular orbital. So stability of the molecules always exists in such a case that whenever NB is greater than Na, then we can say the molecule is stable. If NB is less than Na, then the molecule is unstable. So in a molecule, when you consider the MOT diagram, the bonding molecular orbitals must have higher electrons rather than the anti-bonding molecular orbital. So then we can say that the number of electrons in bonding molecular orbitals must be more and number of electrons in anti-bonding molecular must be less. So this is what the two conditions you have to remember, the stability of the molecule. And nextly, we have some examples with respect to the O2, N2 and all. So just I am going to solve with respect to the molecule. So you have to know that. So when you have the total electron count of a given molecule, if it is up to 14, means it is giving me only 14 electrons. So total O2 if you consider, there it will give me 16 electrons if you consider, because for single oxygen it is 8 electrons and another oxygen will be 8. So overall 16 electrons. So it is exceeding 14. In the sense it is above 14 electron, then you have to apply this this configuration. So this configuration you have to apply, then you have to fill the electrons in such a way that the orbitals I am going to show how exactly 2 1 1 2 you are going to get, and up to 14 in the sense what, so this is what the electronic configuration you have to follow. So this you have to keep in your mind. So just make it sure that you have just let me put the star mark itself here. Okay, so just you can understand it. Okay, so just you have to mug up this, or else just let me tell you one trick also how you can remember. So this is what you have, and apart from this, just let us look at the example. So the MOT of O2, if you look, so this is what overall, with respect to the molecular orbital theory of O2. So we know that oxygen is having 8 electrons, right? So it has 8 electrons, and then so one oxygen where 8 electrons, then two oxygen will be 16 electrons. So overall 16 electrons. Then how you are going to fill the electrons? So this is what above 14. So above 14. So the configuration has to be this one, right? So the configuration already I have shown along with the electrons. So now if I consider two oxygen, so this is one oxygen and this is another oxygen. Okay, so one oxygen 1s and another oxygen 1s. So both are giving one electron, and it is giving me bonding and anti-bonding. So sigma 1s is what? Bonding molecular orbital. Sigma star is what? Anti-bonding molecular orbital. So sigma 1s, sigma star 1s, and 2s of one oxygen atom is giving one electron, and another atom is also giving one more electron. It is giving me where bonding and ABMO, that is sigma star 2s, that is sigma 2s and sigma star 2s. And similarly 2p are also involved in the bonding, where it is giving me electrons with each other. By considering two oxygen atoms, then what I can say overall, so it is giving me bonding and anti-bonding. So this is what? Anti-bonding, this is bonding. Okay, now coming to the electron count, if you consider overall, okay, if you consider overall here, you have this is bonding, this is also bonding, bonding, bonding you have, and this is what? Anti-bonding you have, right? So now coming to the bond order calculation. Okay, so before that, what I had told you, whenever you have the total electron count in a molecule is up to 14 and above 14. So this example is above 14. So above 14 in the sense what? You can just look at the example here. Just let me highlight it. So this is what you have. Okay, so this part, as you can see, 1 2 1 2, this is 1 2 2 1. Okay, this is 1 2 2 1 I can say, and just let me note down it as 1 2 2 1 here. So this is what? 1 2 2 1. So this 1 2 2 1 code is with respect to what? So one orbital you have down and two above, and again here two, again one more here, right? So this is what? 1 2 2 1. So 1 2 2 1. So that is what the code word you can remember with respect to the above 14 electron, means it is exceeding the 14 electron. Then you have to show the orbital picture like this. So one first where the sigma 2pz comes, then goes the pi 2py and pi 2pz orbital. So that is what I can highlight here also. So this is what the sigma 2px is coming first here. So when you have the 14 electron count up to 14 electron, then the sigma 2px will come later, right? So now the sigma 2px you have here, and the pi 2py, and apart from that pi star 2py and pi star 2pz and sigma star 2px you have, right? So this overall what you can say, what we can say, that is one code word you can remember with respect to this, that is 1 2 2 1. Okay, so 1 2 2 1. So this is what the code word for total electron count when it is exceeding above 14. So when it is exceeding 14. So this is what with respect to MOT of O2. So both oxygens, they are combining with each other, and the atomic orbitals are combining with each other, and it is giving me molecular orbital. And now coming to the next example, that is N2 molecule. So in case of N2 molecule, you have where the two nitrogen atoms are combining with each other, and then they are going to form the N2 molecule. And in nitrogen you have 7 electrons. So each nitrogen, then 7 electron, in the sense total 14 electrons you have. So total 14 electrons, and it is up to 14 electrons, right? It is up to 14 electron, in the sense So this configuration you have to follow. So this configuration you have to follow. Then what you can observe here, the orbital is completely different here, right? So the orbital here, it is completely different. So here it is 2 1 you have. So earlier it was the one orbital was down and the remaining these two are above. So now you can see 2, that is pi 2px pi 2py has come first, then comes your sigma 2pz, right? So sigma 2pz if comes first, then it is exceeding 14 electron having molecule. If the pi 2px and pi 2py you have first, then it is what the above like up to 14 electron, whatever the total electron count you have. So now the code word what you can give here, you can give it like 2 1 2 1. So the first one will be changing, the second one will be remaining as it is. So in case of that, it was 1 2 2 1, right? So 1 2 2 1 where you are keeping it constant. 2 1 is keeping constant, only the thing 2 1 and 1 2 you are changing. So 1 to 2 1 is where you are exceeding 14. Okay, so you're exceeding 14 where x will be greater than 14 if I consider, and 2 1 2 1 where it will be equal to 14 or else less than 14. Okay, so this is what the code word overall you can remember with respect to MOT of N2 and O2 molecule. Okay, so these are what with respect to MOT of N2 and O2. Similarly, you have so many molecules, so you have to practice a lot with respect to MOT and Vsepr theory in order to know the shapes and geometry or else the hybridization of each and every molecule. So they will ask you different type of questions and we will come along with the questions also once again. And now I hope I have cleared the chemical bonding concept. And one more thing I had told that regarding the bond order also, so right? So in case of N2 if you consider, so bond order how you will calculate, that will be like 1 by 2 into that is NB minus Na you will calculate, right? So overall you are going to put the bonding electrons, like the number of bonding electrons and the number of anti-bonding electrons. So number of bonding electrons if you consider here overall, sigma 1s you have, then sigma 2s, pi 2px, pi 2py you have. And the anti-bonding how many electrons you have? Only sigma star 1s and sigma star 2s. So this is what that will be minus, that is divided by 2. So how many you have? So 4 you have your anti-bonding. So this is what the anti-bonding you have. Apart from that, how many bonding you have? 1 2 3 4 5 6 7 8 9 10. So you have 10, right? So 10 minus 4. So 10 minus 4 will be 6 divided by 2. So that will be giving me 3 as the answer. So the N2 molecule, if you consider, it will be having 3 bond in a molecule. So this is what you are going to calculate the bond order also. So similarly for the O2 also you are going to calculate the same thing, but there the anti-bonding you are going to consider bit more, right? So where there will be 10 minus 6 divided by 2 you have. So 10 minus 6 will be 4 divided by 2, then it will be 2. Overall you are getting the answer. So this is what the bond order you will get for O2 molecule. If you go and look at the molecular orbital diagram and just look at the anti-bonding molecular orbital electrons and the bonding molecular orbital electrons count, then you will get the answer. So this is what with respect to MOT, VSEPR and overall the chemical bonding concept. So now just let us look at the two examples and then let us wind up. The thing is, the question is like that, the predict the correct bond, like correct order among the following. So they have given the correct general trend already. I had mentioned in the previous slide, right? So just try to recall it. Okay, so what answer you will get? So the four options you have regarding lone pair, bond pair, bond pair, lone pair, bond pair. So which one will come first? So quickly answer me. So what you can get the answer here? So already I had given you the explanation part for this also. Yes, students. Okay. So someone has answered Daytech as option D. Yes. All right. So the option D is correct here. Okay, so already I have mentioned the lone pair repulsion will be more than lone pair, then bond pair repulsion, right? So this is what you have. Now coming to the next question. Next question is The variation of the boiling points of the hydrogen halides is in the order. So they have given the order as HF, HI, HBr, and HCl. So this is what the order you have. And what explains the higher boiling point of HF? So what it explains? So with respect to HF, the hydrogen fluoride, what causes it to have the higher boiling point? Okay, so why it has? So the options they have given, the reasons: the bond energy of HF is greater than in other hydrogen halides, and the effect of nuclear shielding is much reduced in fluorine, which polarizes the HF molecule, and the option C where the electronegativity they are comparing, and lastly it is regarding hydrogen bonding. So which option you can choose, students? So just let me answer. So quickly answer. Okay, someone has answered it as C. Okay, okay. So just let me tell you the answer. So the answer is with respect to hydrogen bonding. We know that what exactly hydrogen bonding? Hydrogen bonding is the electrostatic force between the hydrogen, that is positively charged hydrogen, and the most electronegative element, that is nitrogen, fluorine, and oxygen, right? So between that there will be hydrogen bonding, and that hydrogen bonding is causing mainly increase in the point of the boiling point with respect to HF molecule when we compare with the HI, HBr, HCl. Okay, so this is what you have the reason with respect to boiling point. So the option you have to choose here is option D, that is due to strong hydrogen bonding in HF molecule. So if you consider hydrogen and fluorine, again you have hydrogen, fluorine, where hydrogen will be having partial positive charge, fluorine will be having partial negative charge, and their existence of hydrogen bonding between this fluorine and hydrogen, and then what you can say, partial positive, partial negative charge. All right, so this is what with respect to hydrogen bonding reason overall. And now with this I am going to end this chemical bonding concept. I hope I have cleared every single concept of chemical bonding chapter, which is important for the exam point of view. So if you have any doubt, still you have time, you can ping me in the chat box. Okay, so now coming to the last slide is thank you. I guess you have enjoyed my session, and this is my last chemistry session. Okay, and again we'll come up with few more concepts in the future. Until that, thank you, bye bye. And one more thing I had mentioned you regarding the freebie also, just don't forget to look at the description box. Go for it. Thank you.